So we are absolutely swimming in data, right? Every click, every purchase, every single thing we do generates it. But how do we actually make sense of it all? Well, the answer lies in learning a special language, the language of probability. And today, we're going to learn its grammar so we can start to really understand the story the world is telling us.
This really is the big question, isn't it? How do we find something that looks like truth, or at least make a solid prediction, when all the data we have is, well, it's messy, it's uncertain? And this is exactly where probability comes in. It's not just some abstract math class you had to take. It is our most powerful tool for navigating all the gray areas of reality.
So here's our game plan for today. We're going to start with the basics, this language of data, then we'll dive into the world of chance. After that, we'll learn how to find the center of the story in our data, see how different pieces of the puzzle interact, and, this is the cool part, discover how we learn from new evidence. And finally, we'll put it all together to see the incredible power of building a model. Think of it like this. We're going to learn the alphabet, then form some words, and by the end, we'll be writing powerful sentences that describe the world.
First up, the language of data. You know, when you think about real-world data, it is never ever perfect. It's just full of noise, randomness, and little imperfections. Probability is what gives us the grammar for this noisy world. It provides a set of rules, a structure, to describe, measure, and reason about all that uncertainty, and it helps us turn what looks like chaos into patterns we can actually understand.
Okay, so to speak this new language, we need to learn its most fundamental words. We're going to start with three key concepts: sample spaces, events, and variables. These are the absolute building blocks for this entire field. First up, we have the sample space. Now, this sounds fancy, but it's actually super simple. It's just the set of all possible outcomes of an experiment. If you're about to do something where the outcome is random, the sample space is basically the entire universe of what could possibly happen. That's it.
Let's make this super concrete with something we've all done, rolling a die. The sample space, well, it's every possible thing that could happen. You could roll a 1, a 2, a 3, 4, 5, or 6. A single result, let's say you roll a 3. We call that a sample outcome. Now, an event is just a group of outcomes we're interested in, like rolling an odd number. To find its probability, we just count the outcomes in our event. There are 3 odd numbers, 1, 3, and 5, and we divide by the total number of things that could happen, which is 6. So 3 divided by 6 gives us a probability of 0.5. Simple as that.
Next up is the random variable. Now, this is a really crucial idea. It's basically a way to attach a number to a random outcome. For instance, if we flip a coin, we could create a random variable, let's call it x, that equals 1 if it's heads and 0 if it's tails. It's a bridge, a function, that turns these real-world outcomes into numbers that we can actually do math with.
So now that we have our basic vocabulary down, how do we start telling a story with data? Well, we need to summarize it. Let's look at how to find the main character of our data story using something called expected value, and then we'll find the plot twists using variance.
The expected value is kind of like the center of gravity for our random variable. It's the average outcome you'd expect to see if you could run an experiment an infinite number of times. We calculate it as a weighted average, where each possible value is weighted by how likely it is to happen. Honestly, if you had to place a single bet on the outcome, the expected value is your smartest choice.
Let's go back to our 6-sided die. The expected value is 3.5. And here's the really interesting part. You can't actually roll a 3.5. And that's the point. It shows that the expected value isn't necessarily a possible outcome. It's the long-run average you'd get if you just sat there and rolled that die thousands and thousands of times.
But you know, the average doesn't tell the whole story, does it? We also need to know about the spread, and that's where variance comes in. It measures how far, on average, the outcomes are scattered from that expected value. Think of it as the plot twist potential of your data. High variance means you could see some wild, unpredictable outcomes. Low variance means things tend to stay pretty close to the average, which gives you a much better handle on risk.
Okay, this is where things get really interesting. So far, we've only looked at single variables, all by themselves, but the real world is messy and interconnected, right? So now, we're going to explore how variables interact using two super powerful tools: conditional probability and joint distributions. Conditional probability is an absolute cornerstone of reasoning when things are uncertain. It answers a very specific and very important question. What is the probability of event A happening, given that we already know for a fact that event B has happened? It's our formal way of updating what we believe as we get new information. And this has huge real-world consequences, especially in fields like medical testing.
This table here shows the joint probabilities for a cancer test. That means the probability of two things happening together. So, for example, the chance of testing positive and having cancer is 10%. Now, let's use conditional probability. What's the probability you have cancer given you got a positive test? Well, we take that 10% chance of having cancer and testing positive, and we divide it by the total probability of testing positive at all, which is the 10% plus the 2%, so 12%. And look at that. This tells us that a positive test result boosts the probability of having cancer from a baseline of 15% all the way up to over 83%. That new piece of information dramatically changes the odds.
And to see a more complex interaction, check this out. This is a two-variable Gaussian distribution, which you might know as a bell curve, but in 3D. It's a fundamental shape in all of statistics. So what's so magical about it? Well, if you slice it at any point, basically fixing the value of one variable, the cross-section you get is another simpler bell curve. It's this property that makes it so powerful and predictable to work with when you're modeling complex systems.
And now we have arrived at the climax of our story, Bayes' rule. This elegant little formula is, and I'm not exaggerating, arguably the single most important concept for learning from data. It gives us a formal, incredibly powerful way to update what we believe when we're faced with new evidence.
You should think of Bayes' rule as an engine for learning. Its superpower is that it lets us flip the script on conditional probability. See, it's often pretty easy to figure out the probability of seeing certain data if our theory is correct. But what we really want to know is the other way around. What's the probability that our theory is correct given the data we've just seen? Bayes' rule lets us make that flip.
Let's see this in action with a classic example. Imagine a cracked windshield. We have 3 factories making cars. We start with our priors, that's our initial belief about where a car came from, which is just how many cars each factory makes. Then we get our new evidence, the windshield is cracked. We use the likelihood, the known defect rate for each factory to update our beliefs. After running the numbers, something really interesting happens. Even though factory A makes most of the cars, the evidence now points to factory B as the most likely culprit, simply because it has a much higher defect rate.
So this is the big takeaway. Bayes' rule gives us a way to talk about the probability of a hypothesis M given the evidence D. It's a formal, mathematical way to put a number on our confidence in a belief, and, crucially, to update that confidence as we gather more and more data.
All right, let's bring everything together and connect it to what data analysis is all about, building models. How do we actually use all this probability stuff to find the best model to explain our data? Well, one of the most common methods is a technique called maximum likelihood.
Maximum likelihood estimation, or MLE for short, starts with a really simple, intuitive question. It asks, given the data I'm looking at right now, what's the most likely model or parameter that could have produced it? The whole goal is just to find the version of our model that makes the data we actually collected look as probable as possible. Let's see how this works. Imagine we have this simple set of data points here. Our goal is to find the best possible model, which in this case is just a single number that explains this data. Now, if we assume the data was created with some random bell curve noise, it turns out that finding the model with the maximum likelihood is mathematically the exact same thing as finding the number that minimizes the squared distance to all the data points. And what number is that? You guessed it. In this very common case, the solution is simply the average of the data. All that fancy talk, and it comes down to the average.
And that's not just a lucky guess, it's mathematically proven. For those of you who remember your calculus, if you want to find the lowest point on a curve, you find where its derivative is 0. Well, if you do that for the sum of squared errors, the math leads you to one single precise answer, the average. It's just a beautiful, clean connection between a high-level statistical idea and a fundamental concept from calculus.
So, we've gone on this whole journey, from the basic alphabet of probability all the way to building powerful models that are at the very heart of machine learning and AI today. But you know, this power comes with a huge amount of responsibility. As we use these models to make decisions that actually affect people's lives, in finance, in healthcare, in hiring, we have to stop and ask ourselves a critical question. What are our ethical responsibilities? What are the full implications of the models we choose to build? And how are they shaping our world? That's something to think about. Thanks for joining me.